Hello.
As you can see, if you speak loudly in mountainous areas, it seems like the mountains are responding right back. We commonly call this response an echo. Let's consider another example. Golconda, a ruined fort in south-central India, is situated west of Hyderabad. One of the famous engineering marvels at Golconda is the fantastic acoustic effects used to maintain security in the fort. A hand clap at a certain point below the dome at the entrance of the fort can be heard clearly at the highest point in the fort, located almost a kilometer away. This hand clap worked as a warning note to the royals residing in the fort in case of an attack. Why do we hear echoes? Well, like light, sound also reflects off objects. Reflection of sounds lead to such phenomena as echoes. In this lesson, you will learn about the reflection of sound. At the end of this lesson, you will be able to define reflection of sound, verify laws of reflection of sound, explain the concept of an echo, calculate the minimum distance required to hear an echo, list the applications of multiple reflection, define reverberation, explain the structure of the human ear, define the ranges of hearing for infrasonic sound, audible sound, and ultrasonic sound. List the applications of ultrasound and define sonar. Look at this ball. When it is thrown, look at this ball. When it is thrown on a hard surface, it bounces back. Light as well as sound waves behave in a similar manner. When light rays are incident on a reflecting surface, they bounce back. Similarly, a sound wave incident on a hard surface bounces back into the same medium. This is known as the reflection of sound. According to the laws of reflection of sound, the direction in which the sound wave is incident and the direction in which it is reflected make equal angles with the normal to the reflecting surface at the point of incidence. The incident sound wave, the reflected wave, and the normal at the point of incidence are in the same plane. Sound waves need polished or rough surfaced obstacles to get reflected. Let's verify these laws through an experiment. To set up the experiment, we take two identical hollow pipes, PQ and RS, each about 2 feet long. We place these pipes on the surface of a table near a wall so that their axes intersect at point O on the wall as shown. Then, we keep a clock near the end P of the pipe. Finally, keep a cardboard vertically in between the pipes, so that the sound of the clock at P cannot be heard directly at the end S of the pipe RS. Now we try to hear the sound of the clock from the end S of the pipe RS. The angle of the pipe RS can be changed by tilting it in a horizontal plane about the point O. The sound is very feeble, isn't it? That's a little better. Wow, that's quite clear, right? Oh ho, this angle is not so good. The sound has become feeble again. A feeble ticking sound can be heard through the pipe RS in random positions. Fix the position of the pipe RS at the angle where the loudness of the sound heard is maximum. Let's now measure the angle between the axis of the pipe PQ and the normal to the wall at the point O. This is the angle of incidence, I, for the incident sound wave. Now we'll measure the angle between the axis of the pipe RS and the normal to the wall at the point O. This is the angle of reflection R for the reflected sound wave. You can see that the angle of incidence is equal to the angle of reflection. Now, try changing the orientation of the pipe RS by tilting it vertically. The audibility, that is, the loudness of the reflected sound, decreases. This is because, when tilted vertically, the plane of the reflected sound wave is different from the plane of the incident sound wave. In this situation, only parts of the reflected sound wave pass through the pipe RS. This confirms that the incident wave, the reflected wave, and the normal all lie in the same plane. We already saw what happens when you shout in an open air in the mountains. Let's now observe this boy shouting into a well.
This is an experiment.
Did you hear that? That was the boy's voice reflected back from the water in the well. In our daily lives, we call this sort of a reflection an echo. Thus, an echo is repetition of sound that results as a reflection from a surface. Here's an interesting fact about the origin of the word echo. According to Greek mythology, Echo was a nymph who had the job of talking incessantly to Hera, the queen of gods, so that her husband Zeus would not get caught in his misdeeds. Hera caught on to Echo's tricks and cursed her to only be able to say what others had just said. Thus, reflection of sound can be attributed to Echo talking under the curse, repeating what you say.
Hello?
You may be wondering why you don't hear an echo for reflection of every sound. To explain this, let's observe a scenario where a man standing in front of a cliff shouts, "Hello."
Hello? Hello?
Did you hear that? There was a clear echo. Now, let's see what happens if the man moves closer to the cliff and shouts, "Hello" again.
Hello?
In this case, there was no echo when the man shouted. Why do you think you could hear an echo in the first position but not in the second? Try and analyze what changed in the second situation. Nothing but the distance of the man from the cliff, right? It is the distance that is making a difference. We cannot hear an echo unless the reflecting surface is beyond a specified distance from the source of the sound. In this case, it was the man shouting hello. To find out how this works, let's examine how our brain processes sound. The sensation of sound persists in our brain for 0.1 second. Therefore, to identify an echo, the time interval between the reception of the original sound and the reflected sounds should be at least 0.1 second. So, how much distance do we need between the source of a sound and the reflecting surface to be sure that we will be able to hear an echo? Let's find out. The speed of sound at a given temperature, say 22 degrees Celsius, is 344 meters per second. Consider the echo produced by shouting on a cliff. Let d be the distance between the source of sound, in this case, the man and the obstacle, in this case the cliff. The distance travelled by the sound wave from the source to the obstacle and back to the source is equal to 2d. To hear the echo, the duration in which the reflected sound travels back should be at least 0.1 second. Therefore, by using the expression of speed, the distance travelled by the sound wave is equal to the product of the speed of the sound and the time for which a sound persists in our brain. On substituting the values and simplifying, we get the distance is equal to 17.2 meters. Therefore, the minimum distance required to hear an echo is 17.2 meters. Note, this distance will change with the temperature of air, as the speed of sound changes with the temperature of air. When you hear thunder rolling, the sound continues for some time. The rolling of thunder is due to the successive reflections of sound from a number of reflecting surfaces, such as the clouds and land. This is called multiple reflection of sound. Thus, multiple reflection of sound is the successive reflection of sound from various reflecting surfaces. We find many useful applications of multiple reflections of sound in our daily life. A doctor using a stethoscope to give you a checkup is a very common sight. A stethoscope uses the principle of multi-reflections to help the doctor hear your heartbeat. Let's take a look at how it works. The chest piece of the stethoscope consists of a plastic disc called the diaphragm, which is placed on the patient's body. The sound of the heartbeat vibrates the disc. These vibrations produce pressure waves which travel to the listener's ears through the hollow tubes by a series of multiple reflections throughout the tubes. There are various other applications of multiple reflections. Megaphones, horns, and musical instruments like trumpets are designed to magnify amplitude of the sound and reflect and propagate sound waves in a particular direction. The curved ceilings of cinema halls and conference halls are also designed keeping the principles of multiple reflections in mind. The curve in the ceiling ensures that the sound is reflected to all the corners of the hall, so that there is an even distribution of sound. In some cases, a soundboard is positioned behind the stage so that the sound waves produced are spread across the hall evenly. However, in cases where these halls are not designed properly, multiple reflections can lead to uneven distribution of sound. Let's see what causes this problem. Consider a big closed room where a source S, a speaker, and an observer O are in the positions as shown. The observer may hear more than one reflection of sound produced by the source. This is due to the multiple reflections produced at different locations on the walls and in the room. This can make it difficult for the observer to focus on what the speaker is saying and hear him clearly. The reflected sound is heard until its intensity is reduced to a value where it is no longer audible. Finally, the sound fades off completely. Thus, the observer hears the sound produced by the source persistently till it fades away beyond audibility. This phenomenon of persistence of sound in a closed enclosure, due to the multiple reflections of sound in an enclosure, is called reverberation. Reverberation is generally minimized in auditoriums by covering the walls, the ceiling, and the flooring using sound-absorbent material like cardboard, thick curtains, and fiber. Sound as a concept would not exist for us if we could not hear it, right? Therefore, an explanation of the reflection of sound is incomplete without a look at the mechanism that enables us to hear, the human ear. The ear converts audible sound waves in air into electric impulses that reach the brain, enabling us to hear. Here, you can see the structure of the human ear. The human ear is categorized into three main parts: the outer ear, middle ear, and the inner ear. Let's see how these parts work together to produce the sensation of hearing. The outer ear, called the pinna, allows sound waves to pass into the ear through the auditory canal. At the end of this canal is the eardrum or the tympanic membrane. When a compression or rarefaction reaches the eardrum, it pushes or pulls the eardrum inward or outward respectively due to the pressure on the outer side of the membrane. The middle ear is comprised of three bones: the hammer, anvil, and the stirrup. These bones amplify the vibration and transmit the pressure variations of the sound waves to the inner ear. The inner ear is comprised of various parts, including the cochlea and an auditory nerve. The cochlea converts the pressure variations into electrical signals. Then, these signals are transmitted to the brain through the auditory nerve. These electrical signals are interpreted by the brain as the appropriate kind of sound. Hearing aids help us compensate for any shortcomings. Hearing aids help us compensate for any shortcomings in our hearing capabilities. So, how does a hearing aid work? A hearing aid is a battery-operated device that receives sound waves through a microphone. This microphone converts sound waves into electrical signals, which are amplified by an amplifier. The amplified signals are sent to the speaker of the hearing aid. The speaker converts them into sound waves and sends them into the ear at a volume that the ear can clearly hear. The buzzing of a bee is clearly audible. In fact, sometimes we wish it wasn't so loud. However, though we can see the pendulum vibrating, it doesn't seem to be producing a sound. Look at the boy straining to hear the sound of the pendulum. We are unable to hear some of the sounds produced around us because sounds vary in their frequencies. A human ear can only hear sounds that are within a frequency of 20 Hz to 20,000 Hz. This range of frequency is called the audible range. We cannot hear sounds with a frequency lesser or greater than this audible range. However, the audible range for different species is different. Dogs, for example, have an audible range much higher than that of humans. That's why people have watchdogs. Dogs can hear many sounds that are not audible to human ear. The table shows the hearing range for three animals. Dogs can hear sound waves ranging from 18 kHz to 22 kHz. Rhinoceros can hear sound waves ranging from 0 Hz to 5 Hz. Bats can hear sound waves ranging from 0 Hz to 100 kHz. Sound waves that have a frequency less than 20 Hz are called infrasonic sound waves. These are also referred to as infrasound waves or infrasonics. Similarly, sound waves that have a frequency greater than 20,000 Hz are called ultrasonic sound waves. These are also referred to as ultrasounds or ultrasonics. A summary of the various ranges of sounds is shown here. What does the word ultrasound remind you of? Yes, it commonly refers an ultrasound scan that helps check on the health of a baby in a womb. Ultrasound scanners enable us to obtain images of internal organs of the human body. Even though we cannot hear them with our naked ears, ultrasonic sound waves have a wide range of applications in several fields, such as medicine and industry. For example, ultrasounds are used in a technique called echocardiography. This technique is used to diagnose any defects in the heart by obtaining the image of the heart. Ultrasonic waves are made to reflect from various parts of the heart, and the reflected waves form the image of the heart. Ultrasounds are also used for medical treatment. For example, it is used to help people suffering from kidney stones. Ultrasound waves are used to break the stones into fine grains so that they can be released from the body through the excretory system. In industrial applications, ultrasounds are generally used to clean parts located in hard-to-reach places. For example, in spiral tubes, odd-shaped parts, and electronic components. Here's how the cleaning is done. The relevant object is put in a cleaning solution, and these sound waves are sent into that solution. Due to the high frequency of the waves, the dust and dirt particles detach from the object, leaving it clean and dust-free. Ultrasounds can also be used to detect cracks and defects in metal blocks. Cracks or air bubbles present inside a metal block are invisible from the outside. To detect these cracks, ultrasonic waves are passed through the metal block, and detectors are placed on the other side of the block to detect the transmitted waves. On encountering a crack or an air bubble, the ultrasound gets reflected back, indicating the presence of the defect. Sonar stands for Sound, Navigation and Ranging. Sonar is a device that uses ultrasonic waves to measure the distance, direction and speed of underwater objects, or the depth of sea beds. It consists of a transmitter and a detector fitted at the bottom of a ship. Let's see how it works. The transmitter produces and transmits ultrasonic waves that travel through water and reflect back after striking objects or the seabed. The detector catches the reflected rays and converts the ultrasonic waves into electrical signals, which can be suitably interpreted. The distance of the object that reflected the sound wave is calculated using the speed of sound in water and the time interval between emission and reception of the ultrasound. This technique is useful in determining the depth of the sea and to locate underwater hills, valleys, submarines, icebergs and sunken ships. Let's consider an example where we use this technique to determine the depth of the sea. Let the distance from the ship to the seabed be d. The sound wave sent to the seabed has to travel twice the distance from the ship to the seabed. That is, from the transmitter to the seabed and back to the receiver. Twice the distance d is equal to the product of the speed of the sound wave in water, v, and the time interval between emission and reception of the ultrasound. Thus, the depth of the seabed is equal to half the product of speed of the sound and the time interval. Here is an example of a species that uses its personal sonar to obtain its food. A bat emits high-pitched ultrasonic squeaks that hit the obstacle or the prey and reflect back to the bat's ears. Based on the reflections received, the bat is able to determine the nature and location of its prey. This brings you to the end of this lesson on reflection of sound. In this lesson, you learned how reflection of sound results in echoes and reverberation. You also learned about applications of reflection of sound and the working of the human ear. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard. There's Dennis trying his hand at playing the cymbals. Did you notice how he produced 3 different kinds of sounds from the same set of cymbals just by striking them differently? Let's hear them again, all 3 sounds together. Where do you think the difference lies? The difference lies in the characteristics of the sound waves produced by the vibration of the cymbals. In this case, the difference in the amplitude and the frequency of the vibrations of the cymbals produced different sounds for you to hear. In this lesson, you will learn about the characteristics of sound and concepts such as loudness, pitch, audible and inaudible sounds. At the end of this lesson, you will be able to explain the characteristics of sound, identify how amplitude affects the loudness of sound, explain the concept of pitch, and identify how the frequency of a sound impacts its audibility. Ouch! That hurts!
Sorry, I'm just learning to play. I think I got too enthusiastic. But how could sound hurt?
When you strike the cymbals so hard, the decibel level can go way beyond what human ears can tolerate.
Decibel levels? What do you mean?
Well, to understand that, you need to start with the basics. The characteristics of sound. You may have heard people talk about sound waves. All kinds of sound propagate in the form of waves. These waves are like ripples of water in a pond, into which you have thrown a pebble. Can you see the ripples traveling over the surface of water? To examine the characteristics of such a wave, let's try creating sound waves through an activity using a metallic strip. Here's a metallic strip. Let's fix one of its ends against the edge of a table. Now, we strike the free end of the strip with a rubber hammer. Notice how the free end of the strip vibrates up and down about the rest position, producing sound. You can observe a similar motion in several other cases, like in the pendulum of a clock and the string of a guitar. The pendulum in the clock, however, moves to and fro about its rest position. This to and fro motion is called oscillatory motion. A wave involves oscillatory motion. Now, observe closely to see if you can determine the time taken to complete one oscillation. The time taken to complete one oscillation is called time period. Time period is denoted by T. We can actually see the oscillations of a pendulum. Hence, it is easy for us to figure out its time period. But in case of the metallic strip, the vibrations of the free end of the strip are too fast to notice each of them individually. So, we can say that their time period is very small. Another characteristic of sound is its frequency, or the number of oscillations per second. Frequency is the reciprocal of the time period. The unit of frequency is hertz. A frequency of 1 hertz equals 1 oscillation per second. Therefore, if an object oscillates 15 times in a second, what would its frequency be?
That's easy. The frequency would be 15 hertz.
As the strip vibrates up and down, or the pendulum oscillates to and fro about its mean position, the displacement varies. The maximum displacement from the rest position is called amplitude of the vibration, that is, the amplitude of sound. Now, let's try striking the metallic strip a little harder. You can see that this time the amplitude of the strip is greater.
The sound produced also seems to be louder.
You are right.
So basically, amplitude indicates how high a sound wave can go.
Right. It may also tell us how low the sound wave will dip. It is also an indicator of the loudness of the sound produced. Remember how your playing the cymbals made my ears hurt?
Sorry about that.
Loudness or softness of a sound depends on its amplitude. When the amplitude of vibration is very large, the sound is loud. Conversely, when the amplitude is small, the sound is soft. Mathematically, the loudness of sound is proportional to the square of the amplitude of the vibration.
Can we measure how loud a sound is?
We sure can. The loudness of sound is expressed in decibel. Remember, I was talking about decimal levels of the sound you were producing with your drum. Decibel is denoted with the symbol dB. Let's try to get a better idea of decibel levels through an activity involving some familiar objects. Did you know? The decibel level for normal breathing is 10 decibels, while a whisper from 5 meters measures 30 decibels. Here is a chart of decibel levels of some sounds we are all familiar with. The average sound level in a factory is 80 decibels.
How about the ringing of a telephone?
A ringing telephone equals 30 decibels. But there are some sounds that need to be at high decibel levels, like an ambulance siren that is 120 decibels. In fact, it becomes physically painful to withstand sounds greater than 80 decibels.
I can see how the amplitude of the sound affected you. But how can I see the effect of the frequency on the sound I hear?
Okay, here's an example. Consider a musical choir. A choir is comprised of men, women, and children. Listen to them sing. Can you differentiate between the voices?
The first was a male voice, the next was a child's voice, and the last one was a female voice.
How do you think you were able to make out the difference in their voices?
Well, they sound different.
Yes, they sound different because of the difference in pitch or shrillness. In this group of people, the children have the shrillest voices. The women's voices are less shrill than the children's. but shriller than the men's voices. The men's voices are the least shrill or have the lowest pitch. The shrillness or pitch of a sound is determined by its frequency.
That means the children's voices have the highest frequency.
Exactly. Between the men and women, female voices would have a higher frequency and would therefore be shriller than the male voices. Now, similarly, think of the roar emitted by a lion and the sound of a mosquito buzzing around you. The mosquito flaps its wings at a very high frequency, hence the shrill sound. On the other hand, the lion's roar has a low frequency. It is loud but not shrill.
Frequency of sound enables us to differentiate between the voices of people. Interesting.
That's not all though. Observe that policeman whistling for his dog.
Hey, I didn't hear the sound of the whistle. Did you?
No, but that is a Galton whistle, commonly used by the police. The sound produced by such a whistle is of a very high frequency, meant to be heard only by dogs.
Oh, so human beings cannot hear sounds of very high frequencies.
No. Human beings can hear sounds that have a frequency in the range of 20 and 20,000 Hz. This range of frequency is referred to as the audible range. Remember the activity involving the metal strip? You saw that unlike the sound from a vibrating metal strip, we are not really able to hear the sound of the vibration of a pendulum in a wall clock. This is because the time period of the oscillation of the pendulum of a clock is comparatively larger than that of the vibrating metal strip. This brings the frequency of the sound produced by the pendulum far below the lower limit of the audible range. That is why we cannot hear the sound of an oscillating pendulum.
So the sound of any frequency above or below this range cannot be heard by me?
That's right. Such sounds are said to be in the inaudible range, as they cannot be heard by human beings like you. Sounds that have a frequency below 20 Hz are called infrasound, and those that have a frequency above 20,000 Hz are called ultrasound. Dogs, cats, dolphins, and some other animals can hear sounds that have a frequency higher than 20,000 Hz. Did you know? Ultrasound equipment is used for diagnosing medical problems by obtaining picture of babies while still in the womb. The equipment uses sounds that have frequencies higher than 20,000 Hz. This brings you to the end of this lesson on the characteristics of sound. Now, you should be able to explain the characteristics of sound. Identify how amplitude affects the loudness of sound. Explain the concept of pitch. And identify how the frequency of a sound impacts its audibility. When a tuning fork is struck with a rubber hammer, it vibrates with a certain frequency. This frequency does not change even when the tuning fork is struck with the same rubber hammer harder than earlier. The oscillations of a body when set into vibration and left to itself are called free vibrations or natural vibrations. The frequency of a body executing natural vibrations is called its natural frequency. Every vibrating body has its own natural frequency. The natural frequency of a tuning fork depends on its dimensions. The natural frequency of a simple pendulum depends on its length for a given place. The time period of oscillation of a body is called its natural time period. Once set into oscillation, a body executes vibrations with constant amplitude when there are no dissipative forces. Here, amplitude is the maximum displacement of the body from its mean position. Let us now look at some bodies executing vibrations. When a simple pendulum is slightly disturbed and released, it oscillates. The frequency of oscillation, N, of a simple pendulum is directly proportional to the square root of acceleration due to gravity, G, at a place, and inversely proportional to the square root of length, L, of the pendulum. For a simple pendulum of length 1 meter, oscillating at a place having acceleration due to gravity of 9.8 meter per second square, the frequency of the pendulum is 0.5 Hz. Consider a spring of negligible mass with one end fixed rigidly to a support and a load hung at the other end. When the load is pulled down slightly and released, it executes oscillations vertically. The natural frequency N of the spring depends on two factors: its stiffness, constant K, and mass m of the load attached to the spring. The stiffness constant can be different for different springs. Therefore, for the same load attached to them, they oscillate with different natural frequencies and time periods. When the keys of a piano are struck, various strings of different natural frequencies are set into vibrations. Consider a closed organ pipe, which is a pipe closed at one end and open at the other. The air column in it can vibrate with a certain natural frequency, N, which is inversely proportional to length L of the air column. The air column in it can vibrate in different modes of vibration with frequencies in the ratio of 1:3:5 and so on. Consider an open organ pipe, which is a pipe open at both the ends. The air column in it can vibrate with a certain frequency N, which is inversely proportional to length L of the air column. The air column in it can vibrate in different modes of vibration with frequencies in the ratio of 1:2:3 and so on. When a string is held under tension between two rigid supports and plucked in the middle, it executes transverse vibrations. Stationary transverse waves are set up in the string. In the least frequency mode, the string vibrates with one loop with a certain frequency N. This is the least frequency of vibration that can be set up in the string and is called its fundamental frequency N. The fundamental frequency N of the string is inversely proportional to its length L and radius R of its cross-section, directly proportional to the square root of the tension T in it, and inversely proportional to the square root of the density D of its material. When the string is plucked at 1/4 of its length from one end, it vibrates with two loops, and its frequency is equal to 2n, which is called the first overtone. When the string is plucked at 1/6 of its length from one end, it vibrates with 3 loops. And here, its frequency is equal to 3n, which is called the third overtone. Therefore, we see that as the number of loops in the string increases, its frequency of vibration increases. In stringed instruments, like the guitar, we see that the string held under some tension between 2 rigid supports executes transverse vibrations when excited. Now, let us understand the nature of free vibrations. When a simple pendulum is pulled slightly aside and left to itself, it should vibrate with a constant amplitude and frequency forever. Such vibrations can be realized only in vacuum. However, the simple pendulum executes oscillations with decreasing amplitude because of the effect of the surrounding medium. The surrounding medium offers resistance to the motion, and hence, the vibrating body loses energy continuously to the surroundings. Therefore, the amplitude of the body continuously decreases. The periodic vibrations of a body decreasing in amplitude are called damped vibrations. The rate at which energy is lost by the body depends on the surrounding medium as well as on the size and shape of the vibrating body. Let us now learn about forced vibrations of a body. Consider 3 pendulums A, B, and C of different lengths suspended from a common support. A, B, and C have different natural frequencies of oscillation as their lengths differ. Now, set A into oscillation. You will see that after some time, B and C also start oscillating. However, B and C do not oscillate at their natural frequencies. They oscillate with a frequency equal to that of A. Thus, B and C oscillate under the influence of A. The oscillations of B and C are called forced vibrations. When a body vibrates under the influence of an external periodic force with a frequency equal to that of the external periodic force, then the vibrations of the body are called forced vibrations. Let us now look at some other examples of forced vibrations. When a tuning fork is excited and pressed against a tabletop, the tabletop vibrates. Here, the tuning fork is the external periodic force and the tabletop vibrates under its influence. The vibrations executed by the tabletop are forced vibrations. The tabletop vibrates with a frequency equal to the external periodic force, that is, the frequency of the tuning fork. The table vibrates with decreasing amplitude. The vibrations of the tabletop are spread over a large area. Hence, the vibrating tabletop comes into contact with a greater number of air particles than the vibrating tuning fork. As a result, a louder sound is produced by the vibrating tabletop than by the vibrating tuning fork. Thus, in forced vibrations, when a body vibrates under the influence of an external periodic force, it does not vibrate with its natural frequency, but with the natural frequency of the external periodic force. Stringed musical instruments, like the guitar, have a hollow sound box that contains air. When the string of a guitar is excited and it vibrates, the air in the hollow sound box vibrates under the influence of the vibrating string. The air vibrates with a frequency equal to the natural frequency of the vibrating string, which is the external periodic force, and produces a loud musical note. The frequencies produced in the diaphragm of a gramophone sound box that correspond to the frequencies of the tones conveyed by the gramophone record are forced vibrations. To understand the concept of resonance, let us first look at the types of vibrations that a body can execute, namely free vibrations and forced vibrations. When a body, like a tuning fork, is excited with the help of a rubber hammer and left to itself, it executes vibrations, which are called natural vibrations or free vibrations. Here, the frequency of the vibrating body is referred to as the natural frequency of vibration or just natural frequency. In the absence of any frictional forces, the amplitude of the tuning fork's oscillations remains constant. In the presence of a medium, when the tuning fork is excited and left to itself, the amplitude of oscillations of the tuning fork decreases due to frictional forces of the surrounding medium, and finally the vibrations cease. Here, the tuning fork executes damped oscillations. The periodic vibrations of a body with decreasing amplitude are called damped oscillations. In damped oscillations, as the amplitude decreases, there is a decrease in the mechanical energy of the system. The mechanical energy is lost in doing work against the forces that retard the motion, and is lost or dissipated in the surrounding medium. The frictional forces that retard the motion are called damping forces. A body can also be excited by applying an external periodic force. For example, when a tuning fork is excited and touched to a tabletop, the tabletop also vibrates. Here, the tuning fork is the external periodic force, and the tabletop vibrates under its influence. The vibrations executed by the tabletop are known as forced vibrations. The tabletop vibrates with a frequency equal to the external periodic force, that is, the frequency of the tuning fork. The table vibrates with decreasing amplitude. The vibrations of the tabletop are spread over a large area. Hence, the vibrating tabletop comes into contact with a greater number of air particles than the vibrating tuning fork. As a result, a louder sound is produced by the vibrating tabletop than by the vibrating tuning fork. Thus, in forced vibrations, when a body vibrates under the influence of an external periodic force. It does not vibrate with its natural frequency, but with the natural frequency of the external periodic force. It is important to note that in the case of revibrations, the force is applied and then withdrawn. On the other hand, in the case of the forced vibrations, the force is applied repeatedly at regular intervals, so that energy is supplied to the body being forced to vibrate. Consider three pendulums, A, B, and C, suspended from a common horizontal rubber cord. Since they are of different lengths, their natural frequencies are also different. When pendulum A is pulled aside and released, it starts oscillating. Under its influence, B and C also start oscillating with a frequency equal to the natural frequency of A. Hence, B and C execute forced vibrations under the influence of A. Now let us add one more pendulum, D, of the same length as that of A to this system. When pendulum A is set into oscillations again, B, C, and D start oscillating under the influence of A. Here, we observe that D is oscillating with an increasing amplitude. This is because the natural frequency of D matches with that of A. The vibrations executed by D are a special type of forced vibrations called resonant vibrations. When a body vibrates under the influence of an external periodic force whose natural frequency is equal to its own natural frequency, it executes vibrations of increasing amplitude. This phenomenon is called resonance. During resonance, maximum transfer of energy takes place, and hence the body executes vibrations of increasing amplitude. Now let us look at some other examples of resonance. A swing can be kept swinging by periodically timed pushes. The amplitude of the oscillations remains constant if the energy imparted by the push is equal to the energy lost by the system due to the damping forces. If the frequency of the external periodic force, that is, the push, is equal to the natural frequency of the swing, then the swing oscillates with increasing amplitude. That is, it exhibits resonance. In another example of resonance, two tuning forks, A and B, of the same natural frequency are mounted on the top of two separate sound boxes, such that their open ends face each other. When tuning fork A is set into vibration, the air column in its sound box starts vibrating due to forced vibrations. These vibrations get transmitted to the air column of the sound box of fork B. As the frequency of these vibrations is the same as that of the natural frequency of B, they are picked up by B, which now starts vibrating with increasing amplitude. Thus, B exhibits resonance. Now let us see how an air column in a pipe closed at one end exhibits resonance. We can demonstrate this using a resonance apparatus. The resonance apparatus contains a long, narrow cylindrical tube A connected to a reservoir R of water through a rubber tube T. Tube A contains a graduated scale that helps take measurements. The water level in tube A can be adjusted by adjusting the position of reservoir R. The water in A is brought to the brim by adjusting reservoir R. A tuning fork is brought near the open end of A and excited. By adjusting reservoir R, the water level in A is slightly lowered to create an air column AC. The vibrations of the tuning fork cause the air in column AC to vibrate, and a feeble sound is produced. Now the level of water in A is lowered further to increase the length of the air column. The excited tuning fork is held near the open end of A again. A feeble sound is heard again due to the vibration of the air in column AC. As we repeat the procedure by gradually lowering the water level in A, at a particular water level, a large booming sound is heard. This large booming sound is due to resonance between the frequency of the tuning fork and the frequency of the vibrating air column. If the water level is lowered still further and the same tuning fork is excited and held near the open end, then another booming sound is heard when the length of air column is nearly 3 times that of the length of the air column when the first booming sound was heard. Resonance can also be observed in machine parts. For example, the piston of an engine moves in and out at a particular frequency. The vibrations of the piston are picked up by all the parts of the vehicle. If the natural frequency of the vibration of any part is equal to the frequency of the piston, then it exhibits resonance and vibrates with a large amplitude. The part rattles a lot, the loudest among all the shaking parts, and may even drop out. The rattling stops when the vehicle's speed is changed. Stringed musical instruments like the guitar and the sitar have a large hollow box called the sound box. The sound box is so constructed that the frequency of the vibrating air column in it is in resonance with the frequency of the strings. When the string of a musical instrument is plucked, the vibrations are picked up by the air column inside the sound box. The air column exhibits resonant vibrations and vibrates with a large amplitude. Since the sound box has a large area, a large volume of air is set into resonant vibration, and hence a loud sound is heard. Resonance can make a suspension bridge collapse. If the frequency of the steps of soldiers marching on the bridge matches with the frequency of the suspension bridge, then the bridge would exhibit resonance. The amplitude of the vibrations of the bridge would go on increasing, and the structure would break. That is why soldiers marching over a suspension bridge are told to break their step. When you tune the receiver of a radio or a television set, you are actually adjusting the frequency of the vibrations produced by the inbuilt electrical circuit, so that it is in resonance with that of the carrier electromagnetic wave coming in from a transmitter. Due to resonance, maximum energy is absorbed from the incoming carrier waves, and you can hear a clear sound and see a clear picture. getting a headache from all this noise. Can you please switch it off?
But it's rock music, Mom.
Hi there, I'm Melody. You'd better switch the stereo off. Otherwise, you may get into trouble.
I don't get it. How can she call it noise?
Well, actually, that's not uncommon. What's music for one person can be noise to another. Our attitudes toward sound may differ depending upon the time, place, and other circumstances. In this lesson, you will learn about music, noise, and the ill effects of noise pollution. At the end of this lesson, you will be able to differentiate between noise and music, identify the causes of noise pollution, explain how sign language and technological advances help hearing disabled individuals, and list the measures to minimize noise pollution. We constantly hear different types of sounds around us. However, all sounds are not necessarily pleasing to the ears. Some are harsh and jarring and may cause discomfort. Melodious songs, the rustling of leaves, and the gurgling of a brook are usually considered pleasant sounds. Yet, at times, even a song can sound unpleasant when played loudly.
Then, how would one determine whether a particular sound is a noise or music?
In technical terms, any intolerable and irritating sound is called noise. In fact, the word noise comes from the Latin word nausea, meaning seasickness, referring originally to nuisance noise. On the other hand, the term music refers to any sound that you like listening to. You've heard about air pollution, I'm sure. Vehicles and factories contribute to toxic gases like carbon monoxide and suspended particles in the air. The pollution of air can lead to various health problems.
Yes, I know.
Vote for Mr. Hill. Vote for Mr. Hill. Vote for Mr. Hill.
But how about noise? Can noise also cause pollution?
Sure it can. All undesirable sounds and disturbances around us cause noise pollution. You may have already read about respiratory diseases that can result from air pollution. But not many of us realize that noise pollution can also affect our health adversely. Exposure to excessive noise leads to health disorders like high blood pressure, panic attacks, and lack of sleep. If you are continuously subjected to loud noise, you may end up with a temporary or even permanent hearing impairment. Did you know that noise pollution has effects on the environment too? Military activities, oil drilling, fishing, and the movement of large ships cause a lot of disturbance in oceans. Studies have found that marine mammals like whales and dolphins are very sensitive to this noise. In fact, noise pollution causes deafness in marine creatures. There are many ways of dealing with the effects of noise pollution and hearing impairment in general. For starters, let me introduce you to a new language.
it is a language that uses hands, is it? I didn't quite get it.
This was sign language. These signs said, reduce noise. This is the language used by hearing disabled people to communicate. As you can see, sign language uses fingers to spell out words or communicate different phrases. There is a sign language alphabet and even a sign language dictionary.
So, is noise pollution responsible for causing all hearing problems?
Not necessarily. One would rarely come across a person with total hearing impairment. People suffering from this type of hearing disability are usually born with it. Most hearing impaired people suffer from partial hearing disability. In fact, children who are born hearing impaired need special care as they find it difficult to communicate. They may also suffer from defective speech. Apart from the use of sign language, different technological devices like hearing aids help the hearing impaired lead normal lives.
So, what can we do to minimize noise pollution?
Apart from keeping the volume of your rock music down,
Don't worry. I get the message. I will keep it within limits.
on a more serious note, governments across the globe have been taking measures for noise prevention. Different countries have been following a variety of strategies to reduce noise pollution on roads and highways. These include use of noise barriers, regulation of the speeds of vehicles, maintenance of the road surface since uneven roads cause vehicles to vibrate, limiting heavy vehicles, which cause the greatest amount of noise pollution, use of traffic controls to reduce braking and acceleration, and improvements in tyre design so that tyres produce less noise while driving. The Supreme Court in India had framed specific laws to restrict noise pollution. For example, one of the laws says, "No one shall beat a drum or tom-tom or blow a trumpet or beat or sound any instrument or use any sound amplifier at night between 10 p.m. and 6 a.m., except in public emergencies." Furthermore, the area of at least 100 meters around hospitals, educational institutions, and courts are declared to be silent zones.
But what happens if people don't pay attention to these regulations?
Breaking these laws is generally punishable with an imprisonment and/or a fine. Citizens should take action in that case and lodge a complaint. For instance, you can lodge a complaint against the misuse of loudspeakers to the police control room or concerned police stations. This brings us to the end of this lesson on noise and music. Now, you should be able to differentiate between noise and music, Identify the causes of noise pollution. Explain how sign language and technological advances help hearing disabled individuals. And list the measures to minimize noise pollution.